Low score those tests, I think.
Look, no one has been in my class yet.
Alright, dimming the light, so I'm going to open the windows a little, so we don't like totally fall asleep.
It's not like it's English or something, it's math, right or not.
Alright, so nice jobs on the midterm. Not too much that really concerned me here, so lots of places to make little mistakes. But look over my comments, and if you have questions about how to do any of these things, ask now or come find me in office hours or something. A few general comments. So this, I didn't take off points for this, but I noted this on most people's schematics. Let's say you're drawing a circuit and you've got some input A and you've got things coming off of here and they're going into gates and whatever, right? And you've got a switch. So remember how we make switches. You put a 1K resistor, you wire it to 5 volts, and then we have a switch that can connect this to ground. Okay, so this part up here where you're making a switch, you gotta have a resistor going up to 5 volts. You gotta label that 5 volts your VCC. You gotta have a switch connecting here and the switch pulling you down to ground. So I don't think I've seen any incorrectly wired switches, but I've seen a few where these pieces of this are missing. Okay, so make sure that you've got all those pieces in there. And then if this input is labeled A, put your A next to the switch. Okay, and I didn't take off for this, but I saw places where A was over here, or A was here, or A was here. And then if you want to know which switch is A, you got to trace back and sort of figure out that that's the A switch. So logically, the switch is the thing you're going to move to set an input. Go ahead and stick your label on there. And that just keeps it nice and clear. So if you saw me write ABC somewhere on your schematic, that's what I was referring to. Other than that, no real issues with the circuit design problem. The product is some problem, so I wanted an unsimplified POS and then compact form, which is something like this. You did not have to simplify this. Okay, some people did. Nothing wrong with that except it takes time, right? So I saw K-maps and I saw algebraic manipulations, and those are unnecessary for this. Compact form comes directly from the truth table, right? Just write down all the max terms where you have a 0 in the output. And unsimplified form is just explicitly writing those max terms. One problem I saw a few times, so remember for the max terms, it's the opposite of the minterm case as far as putting bars over variables. So if we want the max term for this first row where A, B, and C are 0, it's just A or B or C. Okay, for a min term, it's A bar and B bar and C bar. So min terms, we complement the 0 inputs. Max terms, we don't complement them, we complement the 1s. So that's a 1 point minor thing. The K-map, make sure that you're doing this ordering correctly, 0, 0, 0, 1, 1, 1, 1, 0. And make sure you take advantage of the don't cares.
So the pi symbol is for product of
Product of
sums?
sums, yeah.
Okay.
Pi as in product, and summation, sigma as in sum. Yeah?
I just have a question about 2.
Mm-hmm.
Are we labeling our inputs by the switches because you mentioned switches in the problem, or is that just a generic kind of rule?
So if there were no switches, if you just had a wire coming in that was A, label that wire A, right? And it's pretty clear, you know, if you label this A, well, it's pretty clear it's coming from this switch, right? But if there's a switch in there anyway, I would go ahead and label the switch. If you want to label both, you know, so that you can keep track as you're doing this, that this is A, that's fine too. All right, and 5 and 6 we talked about, and fuse map. Some people ran out of time and didn't get to the fuse map, but if you got to the fuse map, it was mostly So I think those are the only kind of recurring themes I saw on the midterm, but any questions, feel free to ask.
6 simplifies?
6. Oh, this thing? Yeah, it turns into an AND gate.
Oh.
So you can do that algebraically, or you can write the truth table. But if you don't simplify, right, it comes out like this. This is x bar over here. X bar ANDed with y is coming out of that AND gate. X bar ANDed with y, or y is coming over here. So that's this term here, and then that gets ANDed with x. And then if you multiply through by the x, you get xy or x bar y. And x bar is never true, so this is just xy.
Okay.
Yeah. The other thing on simplification, be careful going too crazy with things like adjacency theorem. Right? This is not the same as A. Okay, we can use adjacency theorem and we can say AB bar or AB is the same as A. Right? And basically what we're doing here is we're factoring out the A. And we know that B bar or B, one of those has to be true. So this is really just A and 1, which is just A. But if you factor out an A from here, what you get is this. And this is not equal to 1. Right? Now, if it was something like that, that's definitely the same as A. Because here we have something BC, and here we have that same something complemented. So adjacency theorem applies there. But if you have bars over B and C separately, that's not the same as BC bar.
For number 6, you said it's useful to use a truth table. How would you use a truth table to show your work that way? Do you just test it out one input at a time, like?
So if you've got it in this form here, you could go ahead and fill out all the possible combinations. So x bar y would be true when y is 1 and x is a 0. So that looks like that. And y or x bar y would be true when this column's true or y is true. So that looks like 0, 1, 0, 1. And then if you AND that with x, you want to know when this column's a 1 and this column's a 1. And that's going to give you this truth table. And if you look at that, you may say, hey, that's just an AND gate. So that's one way to simplify it.
If we were like in a hurry and we forgot to draw the little schematic, can we get 5 points back?
Did I take off 5 points for not having a schematic?
Yeah. For this one?
Oh, yeah. I took off 5 for everyone who didn't have a schematic, unfortunately.
Okay.
But it probably will not change things in the end. Abraham? And Kyle. All right, so any other questions on midterm or what we've done up to here? Including this lab. Yeah.
I don't know if I'm thinking about propagation delays or glitches correctly. Are propagation delays, do they cause glitches or are those two separate?
They can cause glitches. So a glitch is any time you have an unintended state in your outputs typically. And if there's no propagation delays, you probably aren't going to see any glitches. But having propagation delays doesn't necessarily cause a glitch, but it can. So the example we picked on was something like this. Right, so this is x bar, this is x again. This should always be equal to x ANDed with x. This should just be the same as x. So whatever x is, you'd expect y to do exactly the same. But if you figure out the propagation delays, you'll see some skew in y. Okay, but that's not a big problem per se. But if you have something like this, so y is x ANDed with x bar, that should always be a 0. So whatever x does, you'd expect y to always be 0. But that's not the case. If you map this out, you're going to see glitches. I think they're going to be on the rising edge. So your output's going to be different from what your truth table says it should be.
So for the logic gates, if we have like a higher range, in like, as far as the propagation delays go, is that like a better chip because it has a higher or wider range?
In some sense, your best chip would be one with 0 propagation delay, because then this would never be an issue. So suppose that this inverter had no propagation delay. As soon as x went to a 1, you'd have a 1 coming in here, and you'd immediately have a 0 coming out of your inverter. So you'd have a 1 ANDed with 0, you'd still get your nice 0 out. Right? The problem is when x goes to a 1, x bar is going to take a while before it drops. Right, so there's this little period in here where x bar and x are both 1, and so the AND gate gives you a 1. So if we're trying to make very fast circuits, a smaller propagation delay is going to be better. But better is kind of subjective. There's so many factors that go into what your ideal gate would be or your ideal chip. Does that make sense? You want to go through it more carefully? And you can build these and actually look at them on an oscilloscope. You got to get a bit more delay than one inverter. If you put in 3 inverters and an AND gate and then just feed an alternating signal into X, you'll see your output's nice and stable except it glitches every time that your input rises in this case. But we're going to take care of those glitches today.
Just out of curiosity, how much of a hit am I going to take on my grade for turning in my lab tonight?
Tonight, instead of
Yeah.
15 minutes ago, I don't know, 2 or 3 letter grades maybe. I forget what I put in Canvas. I think it's like, I don't know, is it 20 points? Whatever Canvas says. But the labs total, I think, what's the percentage on labs? Something like 15%. And there's 8 labs. And lab 8 is going to be optional, extra credit for lab 8. So if you've had issues with labs in the past and you want a chance to get extra points in your lab component, you'll be able to do lab 8.
Was there something online about a separate extra credit, like SL?
Yes, so there's another extra credit opportunity.
Oh my gosh.
I know, it's just extra credit week. So usually when students are in their last year, they're taking the 200 level CS sequence or the 200 level engineering sequence. And through those 3 courses, they work on what's called a service learning project, an SLP. And it's basically a project that you get to choose on your own, right? Something that you just want to spend a year working on here at Clark. And for computer science students, you know, it could be I really want to learn how to do game development in Unity, or I want to make a new kind of web browser, or I want to write an operating system or a compiler for a new language I'm going to invent. Or if you're in engineering, it could be I want to make a solar-powered mole repeller, or you know, I want to make a rail gun. I want to make something that transfers electricity wirelessly across the room without frying people. So it's an area that you're interested in. It's a project that you decide you want to work on for 3 quarters, and you do some research, and you put together a proposal, and then you just go about on your own schedule and develop this project. And it's a chance to do sort of long-term planning, to set some milestones and track your progress and make adjustments along the way, do some research and learn some things outside of what you normally do in your classes. So it's basically a year-long project. So the final presentation for that is usually the last Tuesday of the quarter in June. And students come and they gather in the digital lounge out there, they put up their posters and bring their show and tell and talk about it. So in this class you can get extra credit if you go and visit that expo, walk around and get signatures from groups that you visit. And there's a sheet, I think, of 24 signatures you can get. So if you visit 24 groups or more, you get whatever extra credit it says in Canvas. I forget how much it is. It's something like that.
Details on that.
Okay. So that's an opportunity in June. And it's also a chance to sort of preview what you're going to do when you're in your last year here at Clark. All right, well, let me tell you where we're going here. So we're going to review what we ended with last week, which was looking at SR latches. So we'll recall what those are, and this is going to take us into something called a D-latch. So we'll have 2 types of memory devices, an SR latch and a D-latch. And then we'll talk about race conditions, which are related to glitches. These are timing issues that you have to deal with when you have signals coming from different places feeding into a circuit. And this is going to take us to talk about something called a flip-flop. And a flip-flop is a glitch-free way to do memory, and it's what we build all of our systems out of. And then we're going to talk about different types of flip-flops, and this will include a D, a JK, and a T. So we'll learn 3 types of flip-flops. We'll talk about timing and the equivalent of propagation delays, but for things that have memory. So this will be things called setup and hold time. And we'll look at timing diagrams. For flip-flops, and this is all feeding into homework that I posted earlier today. And then we'll revisit the 74LS93 once we understand JK flip-flops and T flip-flops, because that's what this is made of internally. And then we're ultimately heading towards talking about state machines, basically flip-flops plus logic. And somewhere over here, we'll talk about lab 6 before we're done today. So we'll go up to the break, take a break, come back, talk about lab 6, and then we'll continue with this program. And Thursday we'll continue talking about state machines, and mostly we're going to talk about analysis of state machines. if we have one of these state machines, we have a picture of its circuitry, how can we figure out what it does? And then next week, we're going to flip that around and talk about synthesis of state machines. Here's what I want my system to do. What circuitry should I come up with, and how do I come up with that? So there's two aspects to this. This week we'll analyze state machines. Next week we'll synthesize them. And then we go on to the really fun stuff after that. Okay, so that's our basic program for this week. So let's start with this SR latch. And I'm moving away from these detailed diagrams where we had those cross-coupled NOR gates, and I'm just going to use kind of a system diagram point of view. So our SR latch had two inputs, S and R, and it had an output Q and an output Q bar. And so if our set input is 1, our flip-flop becomes a 1. Okay, so Q is the output. So this is saying set the flip-flop, the output will be a 1, Q bar will go to a 0. If R is 1 and S is 0, that's the reset. So that says I want my output to go to a 0, and Q bar is always the opposite of Q. And if S and R are both 0, then this thing does not change its outputs. So we could say Qn plus 1, and this is equal to Qn. And for now, I'm going to just say illegal. And it's not that anything goes catastrophically wrong if you set S and R to 1. But logically, you're saying I want to set the output to 1, and I also want to reset the output to 0, right? And both of those things can't happen. You either set it to 1 or you reset it to 0. You can't say I want to do both. So in this state, one of these will happen. Either it'll get set to a 1 or it'll get reset to a 0. But Q bar will also do the same thing, it turns out. And it's just goofy and it's confusing. So for SR latches, we just say don't set them both equal to 1, right? So if you want to set it, turn on the S input. If you want to reset it, turn on the R input. But always leave the other input at a 0. So we want to be able to build memories. So what's a memory? You go to a friend and I say, hey, can you remember something for me? Okay, all right, remind me to buy bread on the way home. Okay, so typically you want to give a piece of information to a system and say, remember this for me. And that's not exactly what this SR latch is doing. This SR latch is saying, hey, whisper into this here if you want me to remember a 1. Whisper into this here if you want me to remember a 0. Okay, that's not quite as convenient. But we can use this as a building block to make something more convenient. So this is an SR latch. But let's build a D latch. So a D latch is going to look like this. It has an input, D, and it has an input that we'll call load, and it has an output Q. And a lot of these have a Q bar, but I'm not going to use that for a while because it just complicates things. So there's a D input, there's a load line, there's the output. And this is like your friend who you say, hey, can you remember a 1 for me? And they say, okay, I'm remembering a 1. Or can you remember a 0 for me? And it'll remember a 0. So whatever value you put on here, if you raise this load line, it basically loads that value into the memory. And then when you drop the load line to a 0, that value is stored inside the memory. So if you want to store a 0, put a 0 on D, raise your load line, drop your load line. If you want to store a 1, put a 1 on D, toggle your load line. Make sense? So here's a timing diagram. So let's suppose Q is low to begin with. I can do whatever I want to the D line. As long as my load line is low, nothing changes. This is the line that says, hey, listen to what I'm telling you on the D input. Okay, now if I set the D line high and I raise the load input, at that point, it starts remembering a 1. And now I drop the load input. And now I can go back to doing whatever I want on the D input, and it doesn't change anything. But over here, if I raise the load input, at that point, the output's going to go low. So all the action is happening when this load input is high.
And like a practical use or two wouldn't be going crazy though, right?
It will be actually. We'll see why. Right? But not intentionally. These things where it's going crazy, those are going to be the glitches that we want to ignore. Okay? We're going to have a hard time eliminating glitches, but what we're going to do is we're going to use this idea to say, hey, don't pay attention to those glitches, right? Only pay attention when I raise this load line. So we'll get there in about 10 minutes.
And why is there even a D if the load is pretty much controlling Q?
It's not. Here the load was high and Q went low.
We'll just catch.
But I mean, it just every time it goes up, it makes it change to something. Why have a D at all?
Oh no. So let me do a better timing diagram. And start off Q low. All right, so all the way over to here, the load line is low. So Q is just going to stay at its current value, which happens to be low. Here, the load line goes high. It looks at D. D is a 0. So Q is going to stay at 0.
Okay. They both have to be up.
And same thing here. And here D is going crazy, but nothing matters because the load line is low until you get to here. At this point, Q is going to match whatever, sorry, it's going to go high, and then here it's going to drop, and then it's going to go high. And then when the load line drops, it's back to ignoring D. So while this load line's high, it's actually following D, right? So this is like a gate, right? You have a gate, and if you open that gate, whatever's coming into the gate gets to the other side, right? It gets into the field, right? When you close the gate, it doesn't matter what's happening over here, what's on this side of the gate is latched. Okay, when you open the gate, whatever happens here happens on the inside. So it's like a doorway, right? When load is 1, the door is open, whatever's coming in goes into the circuit and comes out Q. When load is 0, the door gets closed, and whatever value you have inside, that's what Q is. So this is a little more useful because now we can actually put a data value we care about onto the D input, and when we want to save it, we just raise the load line, drop the load line, and it records it. Now how do we, yes?
What's the difference between a SR latch and a D latch?
So an SR latch, if you want to store a 0, you've got to put a 0 on here. Sorry, if you want to store a 0, you've got to put a 0 on S and a 1 on R. If you want to store a 1, you've got to put a 0 on R and a 1 on S. Here, if you want to store a 0, put a 0 on D, pulse the load line. If you want to store a 1, put a 1 on D, pulse the load line. And when we build things like leading up to computer circuits, typically what we have is, say, an adder, and we want to record the output of that adder. Well, each bit that comes out is either a 1 or a 0. If we have one of these, we can just put that bit into the D input, and pulse the load line. It'll record that bit. Over here, if we want to record a 1, we got to somehow put a 1 here and a 0 here. If we want a 0, we got to put a 0 here and a 1 here. They both store a bit, but this one is an indirect way of doing it. This one we can directly store whatever is on D. But they sound similar because they're actually really close to one another in terms of implementation. But we're not going to design a D latch using cross-coupled NOR gates. Okay, we're done with that for now. What we're going to do is we're going to use an SR latch. And it's pretty straightforward. If you have an SR to build a D, so here's what we can do. Here's our SR. But it's not that simple. Here's our SR. Here's our Q. Pair of AND gates. There's a D latch. And what does this do? If your load input is 0, then you've got a 0 going into both of these AND gates. S and R are going to be 0. Your Q value is stable. Right? Doesn't matter what happens on D. If load is 0, both of these are 0, and we know that if S is 0 and R is 0, your latch output is stable. But if you set the load line to a 1, and I missed one more piece. I need an inverter in here. Okay, if your load line is 1, then if D is 1, you have a 1 going into S and you have a 0 going into R. That's the set. And if D is 0 and the load line is 1, you have a 0 going into S and a 1 going into R. That's the reset. So we're repurposing the SR latch to make a D latch. And you could draw this whole thing, since this is just a pair of cross-coupled NOR gates. You could sketch those, and you'd have 2 NORs, 2 ANDs, and an inverter. But we're going to be more successful if we think of this thing logically as a block that does these kinds of things. And then we're going to think of a D latch as simply a block that does what this does, right? So let me show you a truth table for this. So if the load input is 0, it doesn't matter what the D input is. Qn plus 1 is just Qn, right? The new value of Q is the same as the old. If the load line is 1 and D is 0, Q will be a 0. If the load line is 1 and D is 1, Q will be a 1.
Is it Qn plus 1?
Yeah.
Okay.
So that's just that's one way to express the next value of Q. Right? It's a truth table where we're trying to capture this sequential behavior.
Okay.
So we sort of think of Q at time step n, Q at time step n plus 1. It's an imprecise notation, but that's what we take it to mean. And sometimes you'll see Q and Q star. There's different ways to write it.
So our latches, is this something we're going to build ourselves, or these are gates that already exist?
You can build these or you can buy them, right? They do exist.
Are they in the...
I don't know if we have latches, but we do have flip-flops, which is what we're heading towards. We might have latches too. In fact, you might be using a latch in lab 6. We'll take a look when we get there. All right, so that's a D-latch. So what do we do with D-latches? Well, the adder example is not a bad one. So suppose we have a 2-bit adder, sorry, n-bit adder. Let's make it 4 bits. So it adds 2 4-bit numbers, and it gives you a sum. And I won't worry about the carry out from the end. We'll just keep everything being 4 bits. So how many people here have done any kind of programming? CSE 120?
Minute.
So you have a statement like x equals 5. What you're saying is I want something that we call a variable. I'm going to call it x, and I want you to remember the value 5. So a variable is a box. It's got an x on the front in this case, and it can hold a number. And this is saying I want you to put a 5 in that box. So if there's anything in the box, toss it out, put a 5 in instead. Okay. Now if I say print x, it says see what's in the box, go ahead and print that out. Leave it in the box though. Okay, so peek in there, there's a 5, print out a 5. So this box that can hold a number, your number is a bunch of bits. This would typically be something like a bunch of D latches. So we could build a circuit like this. And I'm going to change the orientation of these things. So I'm going to put the D inputs on the top, and I'm going to put the load inputs on the right. And I'm going to connect all of these load inputs together. And I'm going to take these Q's and send them down to the bottom. And this 4-bit register might be the variable x. Okay, a register is like a memory that can hold multiple bits. So let's say this is what the computer is using to represent x. If I want to set x equal to 5, what do? I put binary equivalent of 5 on these D inputs. I raise the load line momentarily and bring it back down to 0. And now my Q outputs have the number 5. And 2 hours later, my program says print the value of x. It can come to this register. It can say this is x. What's the value stored in there? 0101. That's a 5, and it prints out a 5. So this might be part of what's going on inside your computer. When you have a variable, it could be stored in something like this. It's not, but it could be. Now, what about this? What if we say x equals x plus 1? What are we asking the computer to do, just in high-level terms? Say again?
Pull from memory the value of x.
Okay, and do what with it?
Add it to 1.
Add it to 1 and then
Then paste it.
do it.
Paste it. Send it.
Save it again, right? So as you said, we want x to be equal to 6 when we're done, right? So read the current value of x, add 1 to it, make that the new value of x, right? this is ridiculous mathematically, right? X is never equal to x plus 1. If you put that on a math test in 3rd grade, you get points off, right? But we're not saying x is exactly equal to x plus 1. This is an operation. We're saying take x on the right, add 1, and then assign that to x, right? So this is more properly represented with something like this, right? Take x plus 1 and then assign that to x.
Kind of like incrementing in C.
It's exactly incrementing in C. Yep. Yeah, it's like x plus plus. Now suppose we wanted a circuit that could do this, that could add 1 to x. We've already got a circuit that's storing x. And we have an adder that happens to be sitting up here. Can we put those together and make some circuit that will do this operation, x equals x plus 1? So what might we do? All we gotta do is add some wires. Outputs of what?
4-bit.
4-bit adder?
Yeah.
Okay, what should we do with the outputs?
Connect them to the latches.
I like it. All right, so whatever comes out of the adder is going to the inputs of the D latches. That looks like a good step. What else do we need?
The outputs of the D latches should go to the inputs.
Now we got something happening. So I'm using the A inputs. And this is suddenly a very different circuit from any circuit we've done in this course. Suddenly we got feedback. We've got outputs connected to inputs that eventually come back to those same outputs. We've got these feedback loops. This changes everything. Okay, what about the B inputs? What should we do with those? 0, 0, 0, 1. Why is that? Because we're adding 1. So we're going to connect those 3 inputs to ground. We're going to connect that to VCC. And the B inputs will be 1. The A inputs will be whatever's coming out of our X register. And this is an adder. Yes?
So how do you know what wires to connect, like in what order for the 0, 0, 0, 1?
So
Is
we
it just the binary one?
we have to assume what's the least significant bit and the most significant bit. So if this is least significant, then 0, 0, 0, 1 would be 1. But you got to have that understanding, and this is not always the way it works. There's something called big endian, little endian, and when computers started talking to each other, this caused a lot of hassle. Some computers work one way, some work the other way, and they couldn't always talk to each other. So what do we have here? We have something really miraculous here. So suppose our load line is 0. So the load line is 0, and it's currently outputting 0, 1, 0, 1. The input to the adder, well, the A inputs are 0, 1, 0, 1. So let me mark those. The B inputs are 0, 0, 0, 1. This is an adder, so the output should be whatever the result of this calculation is, which happily is the number 6.
What's driving our load higher or low?
Nothing. Right now it's just 0.
Okay.
Okay, it's grounded out right now. So with that grounded out, we have a 0, 1, 1, 0 coming out of here. And so the D inputs are 0, 1, 1, 0. But does that change the Q outputs? No, because the load line is low. So this system is stable. X is equal to 5 still. Okay, now someone comes along and connects the load line to 5 volts. And this goes high. So what happens in our system?
Depends on how long you keep that high for.
Yeah. Well, what's the first things that happen?
Adds 1.
More specifically. That's the punchline. The load line's only connected to these 4 D latches, right? So what happens to our Q outputs?
They get updated to our current result.
They get updated to whatever's coming in on those D inputs. So we have a 0 here, this will become a 0. We have a 1, we have a 1, and we have a 0. So as soon as this load line goes high and some propagation delay passes, our output becomes 0, 1, 1, 0, and X is now equal to 6.
So would you have in between the D latches and the outputs up top, would you put something there to let you know what is being represented at that time? Or
Like what?
like, I can sit here all day and say, hey, I think this is what's supposed to be coming out of here, but would we have something like LEDs in between?
Yeah, you can put LEDs, or you can put it on a scope, or in practice when you're doing this, there's things called signal analyzers.
Right.
You probably work with signal analyzers. And they have this octopus of leads coming out, like 20, 30 leads sometimes. You can clip them at all sorts of different points in your circuit and say record, and it'll record all the ones and zeros at these places, and then you can play it back and look at it different ways. All right, we have a 0 and 1, 0 coming out of here. What happens next? These come around up here, and now these A inputs are 0, 1, 1, 0. And the B input is still 0, 0, 0, 1. And so this is now doing the calculation. And the output of this adder is now 0, 1, 1, 1. What happens next?
Haven't turned off high.
If we haven't turned off high, right, this 0, 1, 1, 1, which is on these D inputs, if our load line is still high, these are going to get loaded into these latches. And the outputs are going to change to match the D inputs 0, 1, 1, 1. We did X equals X plus 1 again, because now X is 7. And if we leave that load line high for a little while longer, that 0, 1, 1, 1 comes up here. The 4-bit adder adds 1 to that 7, gets an 8, 1, 0, 0, 0. That goes in the D inputs, 1, 0, 0, 0. And since the load line's high, those get loaded into these D latches, and the output is now 1, 0, 0, 0, 8. Now, on a computer, when we say X equals X plus 1, we mean add 1 to X and make that the new value of X. If X was 5, make it a 6. But on our computer, when we say X equals X plus 1, we're seeing something different. We're saying, keep setting X equal to X plus 1, which is kind of like a loop. And it's not really what we wanted to have happen. But the circuit that we've built is basically saying keep adding 1 to X. So one way to fix this is as soon as this 6 has gotten loaded into here, slam that load line down. Set it back to a 0 quickly before that 6 can come around, turn into a 7, and get loaded in here. But the timing of this becomes critical now. Because if we don't leave that load line high for long enough, if we only raise it for 1/10 of a nanosecond, the circuitry inside here probably doesn't have enough time to stabilize, and we can get goofy results. But if we leave it open for 5 minutes, we're going to get a bunch of values coming through, right? Every 20, 30 nanoseconds, we're going to get a new value loaded into here. And what's even worse, what if this path, for some reason, is much longer than this path, right? This poor bit over here might take a really long time to come through. We might not even end up adding 1. We might be adding 1 to the old value in this bit and the new value in these bits. And you can get into all kinds of goofiness. Okay? So this is a nightmare to try to work with. Primarily because as long as this load line is high, whatever's coming in the inputs, that becomes the new value of the flip-flops, and it immediately appears on the outputs. So this is something called asynchronous design. And it's a hot research area. There's a lot of work being done in looking at how you can actually design circuits like this that work in some sort of meaningful way. But it's famously difficult because of all these possible complications. You have to do a lot of work, and it's not what we use inside our computers. So let's take a 5-minute break. We come back at 1. We're going to talk about the alternative to asynchronous design. I'll let you think about what that is. Yeah.
To make this design work, you would need like a perfect environment.
Yeah. And you need to know exactly how long you should keep this thing high and then drop it.
Like some complex mathematics.
Well, yeah, and classic story, you get your circuit and it's working great in the middle of the night. When you finished it, and you come into school the next day and it's 80 degrees in the room, and it doesn't work anymore because the switching times of these things are temperature dependent. So yeah, it's a real challenge. Yeah.